To my 7 fans of this design out there, howdy! Today I'm going to give a brief explanation of how movement works in this game, because apparently I didn't do a very good job of it before with my photos and commentary. So I'd go over it. I thought I'd go over it now, enlighten people as to the relative simplicity of moving between planets in this game versus the real world. Okay, so as you can see, this is Earth and Mars. I've left Venus and Mercury off the display for now, just because it's not relevant what they're doing. This is their starting positions as of January 2025. There's an online calculator let you look and see what the different planetary alignments are at different points in time on which I based this. As you can see, there are different rings on the display separated by the heavy white borders. These are called the orbital regimes. What they are is a means to regulate the sun's gravitational pull and its effect on emission without burdening the players too much. They don't have to deal with that every single turn, only when they cross one of those regime borders. Going away from the sun, of course, you're going to be pulled back and thus lose energy. So every time you cross one of these borders, you'll have to pay a price. Either you'll have to do an additional burn to maintain your current vector, or you're going to have to lose something from your vector. Okay. In addition to that, every ring on the board, even it's the same for any regime. Every regime on the board has a speed limit for every ring within that regime. For this regime where Earth resides, the speed limit is 3, and what that means is if you exceed an orbital velocity of 3, you're actually going to be pushed outwards away from the sun, because you've exceeded the maximum velocity to maintain that orbit around the sun. I call that in the game a forced transition, and you take advantage of that to get other places. That is essentially how a homing trajectory works, is forced transition from one point to another point by exceeding the local speed limit. Conversely, going inwards, if you go under the speed limit, you'll start falling towards the sun. So it works both ways. That's the point. Okay. So how do you figure to get from Earth to Mars? How do you know when it's time to go? That's the question. Now, on BGG, on my blog entry, I posted a chart that's in the player aid for the game. I posted a chart that it's a shorthand, basically, a road atlas that tells you when it's time to go, depending on where you want to go. And I think that'll be a big help to the players. But for those of you who want to understand how the movement works and see whether or not you think you would be inclined to do that sort of thing on your own, shooting from the hip as it were, I'm going to show that. So let's say it's January. Doesn't matter where you start on here, but we'll say it's January and Earth hasn't moved yet. This is going to be the mission that's going to Mars. It's the mission A for the blue player. Now, on the turn that he leaves Earth, he goes up on here with the same vector as Earth. Earth moves 3 spaces every turn. That's because there's 36 spaces on that ring, and so that comes out to 12 months or 1 year for one full orbit around the sun. Since the minimum time increment in the game is 1 month, the planets also have movement. All the planets have their own movement on a monthly basis. Now, Mars is on a ring that is 60 spaces around in order to maintain the same aspect ratio as the spaces on the inner rings and the outer rings. The number of spaces increases as you go out. Number of spaces in a ring increases as you go out. And Mars moves 33 spaces of that 60 every year. Just facts of life. It moves 33/60ths of its orbit every Earth year. So it takes a little over 2 years, a little less than 2 years, I'm sorry, a little less than 2 years for Mars to completely orbit the Sun. So in the game, those 33 spaces are broken down into 9 turns where it moves 3 and 3 turns where it moves 2. So you can see that most of the time Mars is moving 3 spaces a turn like Earth. Not all the time, but most of the time. So anyway, we're going to go to Mars, and we need to know how long it's going to take. Okay, so let's do a mission to Mars and see how long it takes and where we need Mars to be when we get there. And then we can backtrack from that and figure out where Mars and Earth need to be in relationship to each other prior to the launch. So mission A starts from Earth. When he gets put on the board, he has a vector of 3 because that's Earth's orbital vector. And then he's going to do a burn on his first move and go to 4, which is 33% faster than Earth's orbital velocity. Okay, so he's here. Earth moves 1, 2, 3. He moves 1, 2, 3, 4. And because he has exceeded the speed limit of 3 for this orbital regime, and he's exceeded it by 1, he is forced to go 1 ring out. Okay, February, 1, 2, 3. 1, 2, 3, 4, 1. March, 1, 2, 3. 1, 2, 3, 4, 1. Now, we're in the orbit of Mars now at this point. That's what this ring is right here. So that's where we want Mars to be when we get there. Since we did cross orbital regimes, this mission did have to lose energy or use a burn to maintain its current velocities. We're going to lose that energy. We're going to reduce our vector by 1 because we want to be at speed of 3 anyway, because that's the speed of Mars most turns is 3, and that's how you rendezvous with a moving object. You've got to be going the same speed as it. Okay, so this is where we want Mars to be at the end of the mission. So let's put Mars there. And we know it took 3 months to do it. 1, 2, 3. So let's move Earth back to the beginning of the year and move Mars back 9 spaces. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's count on Earth's ring how many spaces it takes to get to Mars. 1, 2, 3, 4, 5. And then we go straight out into this space. So 5 spaces ahead is when we want to do it. Whenever Mars is 5 spaces ahead on Earth's path and straight out. 5 by straight out. Okay, so let's see if that works. So it's January. Doesn't have to be January, mind you. It could be any month of the game. They just have to be in relationship to each other 5 spaces away on Earth's orbital path. So mission A leaves with a vector of 4 after an initial burn. Earth goes 3. 1, 2, 3 for Mars. 1, 2, 3, 4, and out 1 for the mission. February. 1, 2, 3. 1, 2, 3 for Mars. 1, 2, 3, 4, and out 1. March. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, out 1, reduce because we crossed orbital regimes, and we are at Mars with the same orbital velocity as Mars. That is, we've arrived at Mars. That's how it works.